Hello, hello. Good afternoon. All right, Isabella. All right, Rachel. Good afternoon. Hello. Good class to be. Hello, hello, hello. Indeed. All you know. Uh, okay. Yes. Good to see you guys. Hello, Crystal. Or I'm jumping the gun. Okay, we're gonna get to business. Who's it? Sorry. This is the weird part. The weird part. It's all the weird part. Oh, someone. Sorry. Okay. Okay. Hello, hello. What? Okay. Hello, hello. So waiting to say hello, 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 hello. Yes. Okay. I'm gonna start again. So again, good afternoon, Isabella. Hello, Rachel. Hello, 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 Ardell. Hello, Amanda. Hello, Ingrid. Hello, Melissa. Melissa. I mean, right. Awesome. Awesome. Okay. And hello, and hello, Miles. Hello, Leslie. I think. Okay, we're going to get rolling. I don't want to waste your time today, but I'll say again. Well, no, okay. So a couple of things. Here's this weird situation where here we are in class in the middle of an exam, and that is totally what's happening. We're in class meeting together while there's like an exam out there that is due to me, 10:50 this Wednesday. I have to say, the more I do this weird arrangement, these kind of weird take home exams where I meet in the middle of them, the more I actually believe this is a good thing. Like, I know some of you right now might be a little bit on edge on some aspect of the exam or another, or you might be on edge in the fact that I'm talking about the exam, but you haven't looked at it yet because you're like me and you're like that. You could, or you're not, you're on edge because you're not at all on edge and you think the whole thing is like a joke and you don't even know why I keep making a big deal of it, and that makes you edgy. I don't want anybody to be edgy, but I have that impact on people. I'm here to say that if my experience in the other class, like a couple hours ago, was any indicator, I think it will turn out to be very constructive that you all are here right now in the middle of this exam. Like those of you who have even shown up, like, and that's what you're doing, right? You're walking away from an exam and showing up to class, already a decision. Like some of you, it may be very uncomfortable to be here for some of you. Let me tell you, in the other class, it seemed to turn out that it was a wise decision for people to come because like we totally did talk about the exam and we will hear, and you can watch the recording of the other class if we talk about anything different here. um, I'm here to provide more information than you might expect, maybe. We will talk about nothing but the exam all period, so even if it's like annoying or boring at times, like I think, if you're trying to do well on this exam, I think this will be useful. Okay, so a couple of logistical things first. First of all, if you had me last semester, um, then I'm already impressed that you're still here because I don't think it's a secret. I was a disaster last semester about grading. I mean, it's embarrassing. I mean, it truly is embarrassing. I don't want to dwell on it, but I want to acknowledge it because I do want to make clear that that was a bad semester. And I apologize. I want to apologize, but also like I want to acknowledge it because somehow I think indications are that was a bad semester and this is a better one. That is to say, anybody who's handed in anything or everything that all of you have handed in this class so far, small or larger, I think you've gotten back, I hope, by now, unless you handed in the last 2 hours. And with a lot of you have had a lot of exchanges that are very minor on this whole a game, a turn thing. I think it's turned out to be very constructive in a lot of ways, and keep it up, please. And we'll address that too in a minute. But what I'm trying to say is, if nothing else, it's meant as an indication to you. Like if you've done any homework at all, especially if you've done 2 or 3 assignments and you've turned in the game things at all, you know that I am paying attention to you now in a way that I like better, that is more like teaching than what happened last semester. And so you should assume I really am going to look at your exam. Like that's the tone I'm trying to set here. Again, I don't think that was the tone that was set last semester. But I'm really going to look at your exam when you turn it in. And I'm going to look with excitement because I think you guys are on top of this stuff. And I think we're doing stuff this semester that's not easy. And I think you're doing it. So I'm going to take these exams from everybody at 10:50 on Wednesday, right? I'm going to know that I'm going to still try to be helping you with it right now during this period. Oh, wait, sorry. Oh, yeah. Oh, I'm sorry. I keep saying 10:50. I'm sorry. Wait. You're right. I keep saying 10:50 because I'm thinking of another class. No. It's no. Good point. Sorry, totally my bad. Good question, Isabella. And we are here today to clarify things. I keep saying 10:50 because I'm thinking of a different class. No, your exam in this is due at 3:05 for on Wednesday. And let's address that for a minute. Like, because I'm also very loose on, like, even when I try to get all your stuff back, my concept of deadlines is very loose in many, many ways. Like, in fact, let me say again, that when it comes to any assignment, any homework at all, but especially the homeworks that are called game, a turn, you'll notice that you have even gotten some of those that were like backdated for last week or something, which could totally confuse people and cause anxiety. All the more to show you, you cannot be late on these homeworks to me. You turn them in, you get credit. Okay. I'm loose about that on purpose to the point where I'm even backdating some of them because I want it to be that organized. But you turn in those to me whenever you do. And as long as you're being honest and all that, and you get credit. That's with homeworks. With the exam, let me just pause for a second and say I'm going to try to help as much as possible today. I'm going to continue to hope that you guys talk to each other and try to help each other with whatever I say today. You can look at the videos and the notes and all and the solutions and all that. It's not about hide the ball, but it's because I want a really good product from each of you that I am going to look at, and I do need it on time. Like, just to be clear, like it's sometimes hard to predict what I'm going to be strict on or what not, or what I care about, what not. I still want everybody in the room to get an A. I think there's 1,000 ways to get an A, but one of them is definitely to not be late with your exam. You could be late with homeworks. Don't be late with the exam, and so the exam is due right before class on purpose on Wednesday. Again, I'm not trying to waste anybody's time now. I'll get to the substance of it in a moment, but it is true that I want you guys to, whatever you've done for that thing, I want it in for 3:05 on Wednesday, and then we all show up to class, and then we do whatever we do in class. It might be new material. I know that, and really being done with the exam, putting it to bed, and then showing up for class is like your cap to the experience. Like, that's you running through the finish line. And that's one of those little areas, let's be really real now. Like, I'm writing an exam where almost anything that normal people would think of as cheating, you're allowed to do. And I mean it. Like, I don't think it's cheating. I'm asking you to do it, like, helping each other and all that. But let's be clear, and I will grade them and I'll look at them that way, or in the way that I'll explain in a second. But we all also know that this is one of those moments you don't want to be the person that shows up to class 60 minutes in and submits your exam 60 minutes in, or like blatantly doesn't show up to class and submits your exam like at the end of class or something. You don't want to be because you do know that whenever you submit the thing, it does get stamped on Google Classroom. And on this one, I just have to say, that I will care. Like, if you're clearly doing your exam still during class time, the thing about that is that's blatantly something that everybody else decided not to do, right? I'm not talking to anybody in particular. I'm just so you know where the lines are clear. I'm really fuzzy about a lot of stuff and really forgiving. And I have been that guy that has been working through a class period where something was due and I didn't show up to class and was still working on it. And I've been that guy. I know, but I'm not usually that guy, but I've been that guy. And it feels awful. I mean, it really feels like you're letting your friends down. You're like treating your friends like crap, or your peers, when you do that. And really, you don't. Like, I remember the couple of times I've done that because it did not feel good and I'm not proud of it. And don't be that. And like, even if you do, and I'm not saying you will then fail the course. I mean, there's still always forgiveness, but I'm saying then I will have to penalize. Like, there will be points taken off or something. I'll still read your exam. You'll still get a grade and all that, but don't take an advantage that the other people don't have. That's kind of why anyway. All right, so the exam is due. To answer the question, your exams are due 3:05 Wednesday, and then I do expect you to show up to class. If you're here for like 20 minutes, and then you like write me a chat like, dude, this has been quite a week. I have to go like vomit now for an hour. I'm leaving class. I'll totally understand. You could do that too, but just like make a point of handing in your exam and being there. That's part of the experience. And what each of you are doing on this exam now, I'm saying, wait, sorry. Yeah, so it's due 3:05. I'm still just looking at the chat. It's due 3:05 on Wednesday. You still have, tons of time to work on it. There are those, I know there's people in the room that could do this whole thing starting tomorrow night at midnight and could do it honestly and that's fine. But you can be working from now. What was I going to say about that? But what am I like looking for? Because I'm going to go over some corrections and some things this period, and I'll answer specific questions especially. But there was like one big concern in the other class, or one sort of theme was like, how are you supposed to show me like what I'm looking for? I know what the right answers are. I know I've given you solutions to the pre-practice exam, and I know that the regular exam is only slightly different, but a lot of it's similar. And I get, so like, are you allowed to just be like copying my solutions and turning them in? I mean, in a way, yes, folks. I mean, I certainly expect you to consult my solutions. I don't expect you to pretend that you made all of this up. But the main standard here, and you'll know it personally inside if you meet it or not, the main standard is by the time you're writing something down that you're turning into Google Classroom and putting your name on and asking me to read, by the time it's hitting paper, you get it. That's what you're saying. Like, so what you're writing down, you get. So what is your test? Like, what is the test? What are you trying to demonstrate? You're not trying to demonstrate that you have correct answers, because we all have the correct answers. I know the correct answers. That's not the skill. The skill that you're demonstrating is that you get why the correct answers are the correct answers. You're trying to show in your test that you, like, think of it almost more like a research paper or a project or a portfolio. Like, seriously, not to be cheesy, but in a way, that's what this exam is. It's like a portfolio thing where you're taking all my problems and saying, I get these physics problems. We've learned, I may not know all the physics problems in the world. I may have a tenuous grip on some, but these really super important, super emblematic problems, I know so well at this point. I can show you how these problems are solved in physics. I can show you why these solutions are in fact mini proofs. Each one, right? Notice like most of our problems on this test don't really have real numbers in them, or if they're numbers that are real, they're really like super universally known, like the radius of Earth or something. So you're showing in your test, you're like, it's like an argument or a derivation or a proof of this is why we believe these things about the universe. This is how stuff makes sense and makes sense to me. And that's what you're showing me. So the best way to do that is, sure, you could just try to like totally memorize my solutions. If you want to make sure that you actually get them, actually, of course, try to write them out without looking. You definitely know that, you know, if you do that, but you're still even allowed to be looking while you're writing this. So like, what am I looking for? I'm looking for that when you write down, you're doing like what you do in good homeworks where you can tell that I got excited. You're using different colors, or you're skipping lines. You're making things super clear. You're making diagrams even when I didn't think to ask for a diagram, or you're using different colors in, or where I call like MA and MB in the class notes, you call them like MX and MY, just to show that you're that flexible, right? Like basically anything you get in my solutions, if you know that you get it, you know what parts of it are essential and what can be changed without harming the innocent, right? Like, you know, you could change the color of my font and it doesn't change the physics, right? But some of you don't know, can you change a Z to an X and will it still be right? Or could you change this number and would it still be right? Like, but you can show me, like, by more changes you make, if I have an MA and an MB and you get my point enough that you change them to an MS and an MT or something, right? Or you redefine, the more little variation, like, or you put notes. You could even put notes like, I never understood this part, but this part evidently is because, like, if you comment on it, if you put diagram, we all know once we know something, or you break it down into smaller steps, especially anything that you didn't understand before, and then remember how you got to understanding, it's really easy to show you because you can write out what like the confusion was and then resolve the confusion. Believe me, the struggle that any of you might have is if you know in your hearts you don't get any of this, and you're trying to copy, and then you don't know how to show me that you really get it right. It is hard to show you really get it if you don't. And and I will know that. Like, how much I'll take it out on you is another issue, but like, we all know if this were an English essay, and I'll stop babbling for a minute, but this was like a big concern in the other class. I think, like, think of what I'm asking you to give me. You're not trying to fool me into thinking that you came up with these answers or that it's a big achievement that you have the right answers. Like, that's not, you're trying to show me as best you can that you get this. So it's like long extended homework, if you want to think of it that way, or a portfolio. You're trying to, so wherever you really do feel like you get it, especially somewhere that you didn't get it, now you do, break it down into tiny steps, give extra diagrams, extra colors, whatever. And anywhere that you're thin, you can either race through it and hope the other part takes sway for you, or anywhere you're thin, if you honestly, if you think you're trucking through a lot, and there's one part of the exam that you like, you see the answer in the notes and you see it, and like your friends are, but you still in your heart, you're like, but I just don't get, write that in for real. If you can isolate your non-comprehension to that degree where like there's one line that all your friends are telling you to write down, or you keep seeing it, but you don't get, write the line and then say, but I don't understand how this file, like just make it as personal as possible. If that may, okay, that's what you're trying to turn in for Wednesday. And so I'm trying to make this as clear as possible. So it's not hide the ball, but then you show me as clearly as possible that you get this physics that we've done, nothing more, nothing less. Speaking of that, and I will shut up and take actual questions, but now I want to remember a couple other corrections and stuff. One thing is so the exam is 3 problems, right? And you're all submitting your solutions on separate sheets. One thing is in problem 3, you might want to turn to it in a minute, or I might want to share the screen. Oh, sorry, I should be sharing the screen anyway. One thing is in problem 3, part A. So again, problem 3, part A, it starts all of a sudden it starts talking about the moon. Total typo. I totally apologize. That could be very confusing and alarming. All of a sudden it's talking about the moon as opposed to the Earth. And it even gives you numbers like the radius and the mass of the moon. That is a typo. I didn't realize. I apologize. That's confusing. And even if it would be okay, it's inconsistent because the rest of it's about the Earth. So, so please note, and I might ask you all to confirm in a second, I've corrected that. I changed the moon back to the Earth. I've corrected the numbers. I changed the numbers. I corrected it, and I re-edited the document. And I put a comment in, but I didn't change the whole assignment or make a whole. So I don't. You might want to confirm if you open up the assignment now. Did anybody see this comment in the exam itself that I said something about problem 3, the moon? Can anybody confirm whether they knew about this before this class? Like, I'm actually wondering if these corrections go through. Does anybody know what I'm talking about? So I put in the exam. Oh, is that? Oh, Isabel, that's a yeah.
Yeah, I saw it. It's like it's under a comment on the exam page.
Great. Okay. And does that mean, so you saw the comment on the exam page, and does that mean you got notification of that, or you just like because you looked, you saw it? Like,
I didn't get a notification, but I looked at the page anyways to look at the exam, and I did see the comment.
all right, thank you. All right, that's very helpful. So that's totally helpful. And yeah, so to everybody, that means it is there. Like, so that means to everybody, I'm trying to tell you what the correction is, but if there's any doubt in your mind, download the document again because the document's actually corrected. Like, this always makes me nervous because I don't want to upload a new thing and then you don't know which is the exam or what. So, but the correction I'm saying is that in problem 3, any mention of the moon is meant to be the Earth, and those numbers are for the moon. Like, cross them out and look at my upload or look them up or whatever. And you know, if I see that you just use those numbers, I won't punish anybody, but it's not meant to be a trick. It's supposed to be the Earth throughout the whole problem. There should be no mention of the moon. That's like my global correction to everybody. And again, if in doubt, just consult the exam document again and reprint it or re-download it. So that's number 1. Number 2, okay, I'm going to try to say this briefly. This could turn into a big discussion, but wait, should I say this? Like if your biggest, whoever I'm talking to, if in your heart you're kind of working with this, you kind of think that you know what's going on, you even feel like you know what it is to try to show me. But if you're thinking you're edgy or nervous about problem 3, first of all, you're in the right place. Like I would think the place to be the most unsure about would be problem 3. That's deliberate. Like, the exam does get progressively faster and harder as it goes. It's kind of like the first, but so don't feel crazy if you think problem 3 is giving you anxiety. That's also why I'm prepared to spend the majority of the rest of the time trying to help with problem 3. I will start by saying this. Again, problem 3 is ultimately, or especially problem 3A. Okay, 3A is like the wackiest of the whole exam. It's the seemingly most out of left field, 3A. Like, it ultimately is there for a reason, but it would strike me as a student as the most out of left field. Also, it's very long. Let me make clear 3A, problem 3, part A. I am expecting a long response for that, even though, again, it might be challenging because you're trying part A, and I'm tempted to, I'm not sure which screen to share in a second, but part A, I'm asking you to tell me what's the net gravitational effect, what's the net gravitational force on some particle located a variable displacement r, lowercase r, from the center of a solid sphere. Like, I'm asking you to figure out something. It is ultimately a derivation or a proof. Like, there are, I mean, you don't have to do it as a 2-column proof or anything, but really there's givens and then there's inferences that you're coming to along the way. And then there's a final big conclusion. The given, one of the biggest givens of that problem, of problem 3A, one of the biggest givens might strike some of you as new, but it is a given for this exam, and that is that F equals GMM over R squared. Let me say that again. Let me see if I have this written down. Just see, sorry. Okay, yeah, I'm going to get to this. All right. But the equation F equals GMM over R squared, that certainly you can treat as a given anywhere in this exam. You don't have to prove that or anything. That's a law from Newton. That seems to be the way things are in the universe. Like to answer the question why that's true is a whole other class and fascinating, but not our job. So that's a given that F equals GMM over R squared, or excuse me, F equals negative GMM over R squared. That you could treat as a given as the gravitational force between any two particles, between any 2 points of mass. Like they could be between any 2 tiny objects that could be of any mass you want, measured in kilograms, but are each of like essentially no volume, right? That's what that equation is about. Now, what you're trying to figure out in this kind of long journey in 3A, you're trying to put together a whole bunch of particles into a big solid sphere and ask what all of them together would do to some particle located somewhere at an arbitrary location within the interior of that sphere. There's many steps to this argument. There's many steps to this. I am expecting you to tell me the steps. Now, again, it's an argument. I'm trying to teach it to you or have you know it. You can only be so creative with it. Like it's, there's like a step A, step B. And I am in that sense looking for kind of the same structure from everybody. And I will repeat it. I'll say it in a moment. But so you don't have to like be creative, but you do have to show me that you get this logical argument. What you're allowed to know going into the argument is basic math and basic physics, and you're allowed to know that F equals negative G M1 M2 over R squared between any 2 particles of mass. Now, what you're going to try to argue, I might write this down in a second, but like step 1, wait, if you look in your solutions or if you have your solutions in front of you, you'll notice that from this statement about gravitational particles, we then try to reasonably show that we can blow that up into 2 basic but more complicated cases of mass arrangement of gravity. We try to show that we know what would happen if we know what would happen if one point were outside some other point. We start arguing that we know what would happen if one point were outside a big ball. And we also think we know what would happen if one point were inside a hollowed out but spherical shell, right? Like I'm trying to say this slowly. Again, if you get this, then you get it, and I'm boring you. But if you're not sure, like to be as clear as possible, I'm saying what we know is how gravity works between 2 points, F equals GMM over R squared. What we ultimately want to know in problem 3A is how gravity works inside a solid ball, a solid sphere. The way we're going to get there, the way you're going to get there is you're going to show me that you're going to reason your way through how gravity would affect a point outside a big shell, a big ball, and how gravity would affect a particle, a small mass point inside a shell. Okay. Now that case, what a large shell would do to a gravitational point is right here on the board. Okay. You're going to show me as best in your words, as best as possible, you're going to show me why we can approximately argue. So this is an approximation thing. And that's why there's room for you to be convincing about it. It is an argument that we're trying to make well, the ultimate argument that we're trying to show, so I'm saying, because this question came up in the other class, you're first going to show that if you put a particle of mass M2 anywhere within a big empty hollowed out spherical shell, you want to say, and again, here's an answer. It's not hide the ball. The answer is that anywhere within the interior of a hollowed out mass shell, we would experience weightlessness wherever we might be located. If we are a particle called M2, if we're a tiny point mass, anywhere within a shell, a spherical shell, no matter where we are, all the gravity from all of the bits of mass comprising the shell, they will all cancel out and sum to 0 and thereby exert no gravitational effect on us. Now, I'm asserting that this is true. I am not asserting this is obvious. It's not at all obvious. I think it's true, but it's true because of arguments that can be made for it. It's not obvious. So part of your deal in the exam is you're going to not just say this. You're not just going to say that the total effect of a spherical shell will all cancel out to 0. You're going to show me why. And partly because that's how physics works, but also because we need all this for further material in the course. Like, I promise you it's not arbitrary is all I could say, but why? So let me show you why. Well, here's line one. And again, I'm saying this now slightly differently from the way I said it last week, and all of that is maybe slightly different from what's in the solution. Just put them, and you could find any of this on the web in some way, but just try to put this together so you could see in your mind what I'm arguing is. And again, what I'm arguing right now, I'm spending time on because I do think it's the hardest part of the exam, if for no other reason that it is certainly the part that we've spent the least time drilling or practicing in class. Like, I'm totally get that, that's why it's the hardest. So I am trying to expand it right now. If you look at the next page on the board, what my statement is that throughout the surface of a sphere, the amount of mass of any region you cut out of that surface is approximately proportional to r squared. What the heck do I mean? I mean this. I mean this kind of diagram, which, again, you have in your notes from last week. It looks slightly different there, but if nothing else, by the way, I'm going to try to re-explain this right now again because I think it's the hardest thing. But let's say in worst case scenario, it's 3:30. Okay, we've got a little time. Oh yeah, we are on track. Okay, but so I'm going to try to explain this again because I think it's like the hardest part of the exam and the part that you're in the least position to explain to each other confidently. But in the worst, if I try to explain this again right now and 10 minutes later, there's any of you still like who are paying attention, but you're like, yeah, I still do not get this. If nothing else, take from this lecture that I'm telling you what I'm looking to see on the exam and what not. Like, the harsh reality is I do want to see an argument where you actually say that the sum total of all the gravitational effects from this whole shell is zero, like that, like right here, the thing in black. Like, I am looking to see that in your exam in this part, but perhaps I'm looking to see, like this as a step in the argument. But worse yet, yes, I'm looking to see it explained in this manner, in some kind of manner like this, like so, like this diagram that I'm pointing at. So I'm going to give you my version of it now, but then you'll give. I think that I can convince myself, even though I'm surprised. Or let me back up for a second. Like, let me first say that if I were a mass point, so what I'm trying to say is that even if you don't get this argument right now, please know, if nothing else, yes, I'm looking for an argument like this on the exam. Like, okay, that's. But now, what am I saying? I'm saying, say we were located right at the center. If we were M2, a little particle right at the center of this whole shell, I do think everybody in the room, I think, would agree. If we were right at the center, then the net gravitational force on us would be zero. Like, we'd be pulled up by some of that brown stuff. We'd be pulled down by some of that brown stuff. We'd be pulled left, we'd be pulled right. But I think everybody could see if you're in the center, whatever amount you're being pulled up is got to be equal and opposite to whatever you're pulled down because you're equal far from everything. And furthermore, if you're truly in the center, like, where are you being pulled to? I mean, another way of putting the same point, like right now we all have weight because we're being pulled toward the center of the earth. If we already got to the center, in what direction are we being pulled? There's no direction to pull us. We're already there. So I think you can imagine that there, the 9.8 number they're all used to, being the free fall constant acceleration due to gravity. At the center of the earth, the 9.8 number is not 9.8, it's zero. It's a big fat zero. Now, that part I think everybody can see, but not because there's no gravity, but because there's a ton of gravity pulling the same in all directions. Right? Now, if you can see that, now I just want to shift over and say, well, it turns out here's a surprise, but like many surprises in this course, but a logical truth nonetheless is that if we move over to here, I'm saying, like, let's say our arbitrary M2, this particle that we're testing to see like how much weight it has, say it's off center now. So it's like closer to the left edge than it is to the right edge. Now it's still inside. And remember, this is empty space inside right now. I'm talking about a shell, which is part of the argument that you're making in 3A to build up a solid ball. And again, and please also understand, if it seems really hard and weird and new, we're doing this to build to something we need later. Like, you're not going to put all this work in for nothing. Like, it will pay off even after this exam. But anyway, if we're now looking over here, we got all this like mass pulling us, all this mass pulling us that way, up to the left, right? And we do, all this mass is pulling us gravitationally that way. But now what I say is, okay, we also have all this mass over here on the other side pulling that way. Now, without question, there's stuff over there, stuff over there, but now it's not symmetric anymore. It's not like being in the center where I could obviously see whatever's pulling me to the top left, of course, is canceled out with the bottom right. Like, now it's a more interesting question. Now this chunk up to the top left, okay, that chunk that's pulling me is pulling me to the top left. I can pick out another chunk over here on the bottom right, but that chunk is on the one end a lot farther away. Like very, I mean, it's farther away from where I am than the top left chunk. So distance wise, it would seem to be pulling me a lot less. Distance wise, it like, again, we're assuming this. So if I look at that bottom right chunk, the R that it is from me, let's be careful who's me, this little M2 particle right here at this arbitrary location inside. The bottom right chunk is a lot farther from me than the top left chunk. So according to the gravity rule, it would seem to pull on me a lot less. In fact, let me be more specific, and this is something you could write down in your way. To be more specific, if that thing to the bottom right is twice as far from me as the thing to the top left, right? Like if the R that is away from me is twice as big as the R that the other one is away from me, then according to just straight gravity, just looking at distances, I almost want to ask you guys this, but I'm almost afraid to because we're reviewing for an exam. So I just want to be clear, but you might want to think in your mind right now, like pause the video or whatever. Like if the bottom right chunk is twice as far away from M2 as the top left chunk is, then I'm just going to say right now, on that basis alone, it would pull 4 times as weakly. Now, please hear that. Like, please hear that loud and clear, right? And somehow you'd put this into your words, your own words or diagram, or whatever, in the solution, especially because here I am just saying it. So you've got to get it. I don't know how to write it down for you. The bottom right chunk, if it's twice as far from M2 as the top left chunk, then it would pull 4 times as weakly, 4 times if it's twice as far. Or if it's 3 times as far, it would pull 9.
You're fantastic.
It would pull 9 times as weakly. Hang on. Can I do that? Right? Why am I saying 2, 4, 3, 9? Because of squared, because R squared is in the denominator squared. So according to that, any chunk that's twice as far away would pull 4 times as weakly because it's in the denominator, 4 times because of squared. Now I'm trying not, I hate to beat a dead horse, but of course I love to beat a dead horse, except I don't because that's gross. But why am I saying all that? That would be the end of the discussion. That would be the end of the discussion. That would be your proof, or halfway through your proof. It would say that the bottom right chunk is pulling less on the top left chunk. So then according to that, they wouldn't balance each other out. Like any particle over here at M2 would go flying up to the top left because the bottom right was pulling it 1/4 as weakly. However, the other side of this that I'm trying to argue, that I tried to argue last Friday, that I'm trying to argue now is, wait, this shell is supposed to be uniformly dense. This uniform density thing is like big for something that's like permeates a lot. If we believe, which we do, if it's a given that this whole shell is uniformly dense, meaning whatever thickness, like whatever mass per unit volume it has over here, it has the same mass per unit volume over there. Meaning if you take 2 cubic centimeters from over here and ask how much mass you find, you better find twice as much mass as if you were only looking at 1 cubic centimeter down there, right? That's what uniform density means. So we're saying for any little chunk of mass A in a certain volume A, the ratio of mass to volume, the density, better be the same as for any other chunk of volume and corresponding mass you pick, like these two that we're talking about. Call this one up here MA then, and call this one MB, okay? And I'm not talking about 1 and 2, A and B, because they're like pieces of this now that I'm comparing. What I'm saying on the next page is, okay, well, maybe I'm skipping. I'm saying mass per volume is a ratio, is a constant ratio. Now, this is a shell that's uniformly dense, therefore it has uniform thickness, right? This shell is not getting thicker over here than it is over there. Therefore, however these two things compare in volume really simply comes down to however they compare in surface area. Like one volume is 3-dimensional chunk of space. Each one of these is identical in one of the 3 regions of space in thickness. They're both the same thickness. So if one of these things is bigger than the other, it has to be bigger in surface area, okay? The extent to which it's bigger in surface area is exactly the extent to which it's bigger in mass. Uniform density, meaning if I choose twice as big, as wide a slice over here as over here, then it's going to be twice as massive because this is uniformly dense. Twice as much volume should mean twice as much mass. Therefore, twice as much surface area is going to mean twice as much mass. because the thicknesses are the same. That's what I'm saying right here. See, again, if you're following this, you can see that this is enough, a lot, that for you just to show me that you're following it is a fair challenge. Like, you earn your A by showing that you get this, not by showing that you made it up, not by showing that you can parrot it, but just showing that you get it. There's 1,001 ways to do that for each one of these. Anyway, so I'm saying now, and especially even just like, if you don't get it, like, look at my other, you know what I'm saying. But here, what I'm saying now is, okay, mass of region A per surface area of region A must be the same as mass of region B per surface area of region B. That's a mathematical way of saying, again, if I want to compare these two masses, all I have to do is compare their surface areas. If one's surface area is twice as big as the other, then one's mass will be twice as big as the other. Well, the surface area of a sphere is 4 pi r squared. You can accept that as given too in the exam if that's helpful. Like, the surface, and I think it is actually written on the front page, the surface area of a sphere is 4 pi r squared. So that means the mass of A is 4 pi r a squared, approximately equal to mb to 4 pi rb squared. Now, I've shifted to an approximate equal sign. I'll explain the technicality of that at the end. I'll explain why, because technically there's an approximation I'm doing here, and that's fine, and you're doing that too. But to continue with the logic, then that means that, to go back to the picture, like this chunk, the bottom right chunk, compares in mass to the top left chunk by precisely the same amount as the square of its comparison in radius. Like, the mass goes as a function of 4 pi r squared. Mass is proportional to the surface area, and the surface area of a sphere is proportional to r squared, the square of the radius of the sphere. So what this is saying now, what I'm saying now, is by an independent, just by geometry, the mass of one of these pieces is proportional to r squared, yet the gravitational force exerted by each of these pieces is inversely proportional to r squared, right? Like, the first argument we made was, if one piece is twice as far as the other, the first argument we made was that if the bottom right piece is twice as far from M2 as the top left piece, then it would pull gravitationally on M2 by 1/4 the strength. And that's true. Like, we said that, and I'm repeating it. Now I'm saying, however, if bottom right piece is twice as far away from M2 as the top left piece, then by our geometry argument, then the bottom right piece is four times as massive as the top left piece, because the mass goes as surface area and the surface area goes as 4 pi r squared. So if the bottom right piece is twice as far away from M2 as the top left piece, that means on the one hand, each bit of mass is pulling 1/4 as strongly. On the other hand, there's 4 times as much mass to do that. So the two effects, if all this is perfectly true, then those two effects perfectly cancel each other out. And I'm arguing then, as strange as it is, and it is strange, but I'm arguing then that wherever you are in the interior of a hollowed out, like of a uniformly dense spherical shell, wherever you are in that, you're weightless. The total gravity on you is 0. Like, you're being pulled in every direction, but yeah, exactly the same way. Because in short, for any piece that's pulling you to the top left, there's a piece to the bottom right that is bigger but farther away by exactly the right proportions to cancel it out and leave you with weightlessness throughout an entire mass shell. That's what you're actually, now again, this is one piece of quote problem 3 part A. You would argue that. Then you would argue, I mean, just to like wrap this up now. So you would argue that in your way or somehow. And again, if you get what I'm saying, and your biggest concern is now how to get that across without looking like you're copying, all you do is write down what you get, right? If you don't get what I'm saying, then you know your job is to try to make sense of this by talking to someone else until you get it. But like, once you get it, you'll be able to get across to me whether you get it or not. It will naturally happen. Well, okay, this was all what I was just saying. Sorry, okay, I'll get to that in a minute. So you would argue all this, but just to now tie it together, that's all an argument for why within a shell, the total gravitational force is 0. Now you also similarly, much more quickly can argue if you're outside the shell, the farther away you get from that shell, the more the shell resembles a point of mass. Like the farther away you are from a circle, I mean, a circle has the same symmetry as a point. That is, it's spreading out equally in all directions. So the farther away you get from it, the more you see how it is affecting the universe equally in all directions, whether it's a circle or a point. And therefore, if you're outside the shell, all the total mass of the shell will all pull on you as though it was all coming from the center, one big piece of mass just located at the center. And you take those two statements together now. Now, I know this is, it's not nothing. Statement number one, if I'm inside a shell, the total gravitational effect on me is nothing. Number two, if I'm outside a shell, the whole shell, the total gravitational effect of the whole shell will be as though it were just a point at the center of that shell. And you put those two things together to say, therefore, if I'm somewhere within a solid sphere, right? And now this is finally the question of part A. And again, it's the hardest part of the whole exam, I think. Of part A, problem 3, is if you can convince me somehow reasonably that on top of a ball, the whole ball acts like a point at its center. And if you're within an empty ball, then you feel nothing. Then if you're within a solid ball, here's the argument. If you're within a solid ball, if you're M2 somewhere at variable displacement R from the center, then you are in effect trapped between two cases of mass, the two that we just argued. In other words, if you're somewhere in the solid interior of a solid globe, then in effect, you're standing on a smaller solid globe while this big shell is around your head. Like, and you really, if you can picture what I'm saying, that's really huge. It's important. I'm saying being somewhere within a solid ball is equivalent to standing on a smaller concentric solid ball while there's a hollowed out shell of a ball around your head. Like the shell plus the smaller ball makes the whole ball, right? And it's important to say that because then we can analyze what's inside us. Then if we're inside a solid ball, we say, oh, all this cancels out because we just argued that all of that cancels out, and all that's left is F equals GMM over R squared from this smaller m. So what we do, and I did this already in the solution, so I don't want to confuse things by doing it again right now, but what you literally do is you solve for that smaller m, the subplanet, the enclosed sphere that you're standing on. You get it as a function of lowercase r and capital R, and plug that into F equals GMM over R squared to finally get what gravity is doing when you're inside a solid sphere. You do all of that. Again, this is the answer. Like, so if you're paying attention right now, like this is meant to help. I'm not trying to trick you. Like if you're looking at the solutions now, I'm trying to explain that's what they're saying, right? But you do all that to finally get an answer. I'll even write down the answer right now, actually, so I can, sorry. Hold on. Hold on, I'm just gonna look at the time for a second. I think this is, yeah, we have, okay. So I just wanna make this as clear as possible again, especially if I'm gonna just like talk like this. What I'm about to write down are in effect, the skeleton is the skeleton of what I think the final steps are of A. This is just the final steps. This is just a skeleton. It's like my version. So I'm not saying you have to copy this exact, but it's again, it's not hide the ball. It's like, if this makes sense to you, then you'll know kind of what you have to get to the end. I'm saying by the end of, and also so you'll know when you've reached an answer, what the point is, like you're trying to get the net gravitational force. The key is we're looking for an expression for gravity that takes in lowercase r as an independent variable and a bunch of constants and spits out a force, right? Okay, and I'm going to get Ardell in like 1 second. Sorry. So I just want to make it as clear as I can. We're looking in part A, like you have an answer once you have an f function. that much like this one written down is f as a function of lowercase r. Only it's not going to be that one. And I'm going to get Ardell in a second. I guess want to say, but but that's what is true. That's what's true between any two particles. And what you're going to end up doing is you're solving for m enclosed. Like when I say, and I don't want to forget, but I just want to do this because it's early onset Alzheimer's or ADHD, whatever. I'm saying, and undoubtedly, by the time I finish this whole thing, I'm gonna be like, yes, Ardell, she's gonna be like, someone's waiting outside the waiting room starving, and because you have ADHD, they just like got checked into a hospital. Okay. What I'm saying is, just to, I'm saying when I'm saying in the end, what we're saying is the gravitational effect of somebody within a solid sphere is ultimately just the gravitational effect of the ball that they're in effect standing on, like only the dirt below their feet. That's what we're arguing here, or that's what you've been arguing, that if you want the total effect of everything around them, all that's going to matter is what's below their feet. So as long as you can get so that's what I'm calling mass enclosed. And again, so what you do to finish this problem is you've gotten an expression for m enclosed. You ultimately will find, I'm skipping steps here just so, but you know where you'll ultimately find that, and again, I will get back to, we'll get something like this. So you plug that into this. And when you plug that in, you find what you find, and then this is where I'm going to get Ardell, but what you want, the point of all of A, your final answer to A, you'll know what's going on is if your R squared that was in the denominator eventually ended up being an R that was in the numerator. And if your negative sign is still there, you've done something right, because now you've shown that what gravity does inside a solid sphere is totally act like Hooke's law. Like it exerts a force that's not inversely proportional to the square of a distance, but is directly proportional to a distance itself. That's Hooke's law. That's an oscillator. Like that's your conclusion in part A, is that. Okay, now I'm going to pause for a second. Ardell, I'm sorry. Ardell.
That's okay. I was having a hard time getting this, and I still kind of am. But this is going back to when you put on the screen that FGR is equal to negative G M enclosed M2 over R squared.
Oh, yeah.
This might be a little redundant, but I was just wanting to make sure that I was following you, that M2 would be the big circle, like the big one, right?
Oh, great question. Wait, this is a great question. So the answer is actually no, but it's exactly the right question. Okay. No, this will help a lot of people. No, and we need this. No, I'm glad you asked. All right. M2, lowercase, and I will go back and make a picture of all this in a second, but lowercase m2 actually stands for the little particle of m, the tiny particle that's essentially you, the object that is sitting in the middle of all this, experiencing this, like the little dot. Hold on, let me go back. Yeah, so M2 is actually this little dot here, located at the arbitrary place somewhere within, the hollowness, the empty interior. So M2 is what we might call the test particle, or the receiving point mass. M2 is the little object that is experiencing all the gravity that we're trying to calculate here. So in the original instance, so let me even, so we always need two things to experience gravity. If M2 is the little dot that's like experiencing the pull from the big mass, then M1 is meant to be the original given whole entire, in this case, spherical shell. Like M1 is the big round ball, right? Okay, but there's a reason that the reason Ardell's asking, the reason you're asking, is all of a sudden it's true in this problem. I've now introduced a million other M's. I introduced an MA and an MB and an M enclosed. There's definitely a good reason to be confused here or to like want to clarify this. So I'm going to say a little bit more. I'm saying in general with gravity, by M1 and M2, we just mean the two arbitrary chunks that are pulling on each other, and they're both always pulling on each other, but generally, since they're random chunks that we're talking about, one will be a lot bigger and one will be smaller. Whichever one's bigger, we call M1. Like we just randomly call whatever's bigger M1, whatever's smaller M2, and they're both pulling on each other. But generally, what we're paying attention to, we as physicists, generally we're thinking of the big M1 as pulling on the M2. Like the M2 is also doing it back. But like in a typical case, like M1 might refer to planet Earth and M2 is like me or the rock that's falling toward planet Earth or something. So generally M1 is the big given thing that's probably not going to move much. And M2 is the smaller thing being pulled toward it. But now where I make things complicated here is I'm trying to argue to all of y'all, I'm trying to argue what the net effect of all these little pieces of M1 would all have together onto M2. So then I divided M1 into two regions, MA and MB, and started talking about them for a while, and that gets confusing. But then I did all of that to ultimately then say, and this is where I think a lot of people are probably confused or generally are, I'm ultimately then saying, okay, if I want to know what's happening to a little particle, M2, like a little piece that's now not just inside the empty space of some shell, but if I picture some little piece inside a solid ball, like, so now I'm talking, which is the actual original question of the exam. So now if I have so this is like plum pudding, like it's stuff everywhere. But if I'm asking now the question, what if there's like some little dot called M2, some little particle, like a rock or like me, but just something that we're testing to see how much of a pull of gravity would experience. And when I say how much of a pull of gravity, in part what I kind of mean like is on the surface of the Earth, it experiences 9.8 G. You know, our weight is our mass times G, 9.8. But at the center of the Earth, I think that 9.8 number would be 0. So what we're trying to figure out is like what happens to that 9.8 number, or what happens to the total effect of gravity on some M2 located here amidst all this plum pudding, all this mass all around it. And what we're ultimately saying now, possibly the most confusing thing of all, is we're saying if that little piece were there, it could imagine itself. So if you put some random piece at some random location, lowercase r, amidst all this plum pudding, what we're kind of saying is that piece is in effect trapped between a big like donut, a big blue shell around it, and this big red ball underneath it. And I'm ultimately calling the red ball underneath it M enclosed. Like it's not a real thing. It's not actually a planet or something. It's just the region of the planet that all falls below the location of M2. And what I'm ultimately arguing here is M2 is sitting there on this subplanet with a big shell of a thing around it on the outside. It's like there's a shell above its head and there's like this smaller planet below its feet. All the shell, all this blue stuff, all this blue stuff, all this shell, all cancels to 0. And that's from that argument that I made before with the 4 pi r squares and stuff cancels to 0. That is not legible, but that is cancels. But the red stuff below your feet is what's left. It's like you're like nothing that's over your head would affect you, but the stuff that's below your feet do affect you. And so it's as though, so the gravity you experience is the total gravity that you would experience as though, in other words, instead of, in the final analysis, I'm saying, instead of all of M1 all pulling on this little M2, it's only a certain portion of M1. It's only the enclosed portion of M1 that's pulling on to M2 because everything outside of M2 cancels. So if only we had a way to write out M enclosed, we could substitute that in, and that would give us our answer for the total effect of gravity on M2. So there are a lot of M's flying around. I don't know, but M1 ultimately refers to the whole original given thing. M2 is the tiny particle that's experiencing the force, and M enclosed means all of mass below the location where M2 is. Does that make any sense, Ardell? Or
Yes, it does.
okay, it's a good question. All right. I know this takes a while to sink it. Okay, I'll accept that. Thank you. All right, wait. So that's that. I'll go as long as I'm talking about this. And again, this takes a while to, all of you just like, yeah. I mean, the eye on the prize, what we're trying to do is ultimately get an expression that looks like this at the bottom. The whole, and so all of a sudden there's an r cubed in the denominator, but remember that r that's in the denominator is the given constant radius of planet Earth. So even though it's being cubed, we talked about this before, that's just a constant number being cubed, that just makes a bigger constant number. There's nothing particularly interesting anymore in the denominator, but the variable r has now shifted to the numerator and is now like to the power 1 rather than the power 2. And those steps of how that happened are in the solution. Like you have to look at those. I mean, I didn't just do them here, but therefore we then say, oh my God. Well, again, here. So that's part A, right? That's part A. I mean, it's not all of it, but that's about part A. But then then you get to part B, where it asks something about time. And it's like, what does that have to do with time at all? But what we're saying here is this. If we're saying now, right? If you drop a rock into a tunnel now, like going through the Earth, the only force on it is gravity. This is free fall now. So the only force is gravity. The net force is gravity. So gravity equals MA, and this is M2. Like, so if you drop some rock, call it M2, into a tunnel now, like carved all the way across the planet, we all of a sudden have this situation where remember, acceleration by definition is second derivative of position with respect to time. Now here we have a case where position happens to be measured with r rather than x or rather than theta or rather than z. It's an r, but that's what we're trying to recognize here, that our position variable happens to be, called r here in this context. But this, anyway, but the second derivative of r is what we call a. So we have
a la
Oh, sorry. Wait, I just started writing the wrong thing. I'm sorry. I'm missing the whole point of what I'm doing. No. So what is supposed to be happening now, ideally by Wednesday, is okay, you do this romp and frolic in part A, which is like all of a sudden you're talking about gravity and doing all these things. But then in the end of the day, the gravity force is written in this way that's linear with respect to position. If you're careful and you realize, oh, yes, acceleration is still the second derivative of position with respect to time, it looks like we have a situation here where the second derivative of position with respect to time is directly proportional to position, but with a negative sign, i.e., this is our good, right? This is our good old friend harmonic oscillator. And that's like why we're doing all this. And if you've been following, like, so if you go back to part one of the whole test or whatever, that means that we've got something that's going back and forth as a harmonic oscillator at some constant rate of angular frequency omega. And what's omega got to be? The square root of the constant in this differential equation, right? Again, this is but this is how it all ties together, right? So according to this, and I'm doing this a little bit fast now because I think you can get this and you can see this and it's in the solutions, but like once you did all this work to see that even gravity can fit this form under these conditions, and they're sort of are weird conditions, but they're not really that weird. We're just saying if you go inside a planet rather than outside, all of a sudden gravity is acting like Hooke's law, like a spring, and anything that's subjected to it will oscillate harmonically back and forth. I'm looking at the time at an angular frequency, which is the square root of the proportionality constant in this differential equation, i.e., to make it as clear as I can, i.e., would be a harmonic oscillator of angular frequency square root of gm over r cubed, because all those are constants, right? Therefore, if that's the angular frequency of some particle, then its period, well, I'll just leave it. Then its period would be 2 pi over the angular frequency. And if I'm asking how much time will it take for this thing to go all the way across, what I'm in effect asking for is how much time it takes to do a half period, because a period would be there and back, right? Period is a full cycle. If I want to know how much time this thing will take to get across the whole tunnel, I want a half the cycle. And let me say again, if you're paying attention right now, one of your rewards for like sitting here and paying attention is and especially if you paid attention to the correction to the test, it's all supposed to be about the Earth, not the moon. So I'm telling you right now, if you do this correctly, this part B, the answer you should get is 42 minutes. That is the correct answer. I'm 42 minutes, but you're trying to show that you get that that's correct, not just trying to pull out of a hat. So, but you'll know you're doing it right. And now I'm saying 42, not 84. I'm saying if I ask in the test, which I did, how much time does it take to get across? That means go there without coming back. A period is going there and back. If you put in the proper numbers for the mass of the Earth and the radius of the Earth as given in the test, and you convert to, like, if you're careful with conversions, and I'll even warn you right now, if you just plug the numbers in, I mean, it's a little bit of a pain. It's also why it's an exam. If you put the numbers in and you're careful in the square root and the cube and everything, you'll get a big number. In fact, you'll get a number like 8.64 times 10 to the fifth or something. That's in seconds, right? Because everything you're putting into the square root thing, or like kilograms, meters, and second squares, they're like newtons and stuff. So you'll get some number in seconds. Divide that number by 60, you'll have minutes. If you get 42, you've done it right. The answer to this is 42 minutes. But I'm all okay, and hopefully I'm sort of helping. But again, you're trying to once you get it, you'll get it. And you'll be like, oh, I get it. And then that's what you're showing me. Until you get it, like work with it until you get it. But let me go a step further and say that you'll really put this whole exam together. Like, I think you'll really, your efforts in part one will all be paid off and stuff. When you get to the final thing of all this, like, sorry, yeah, let me pause for a second. No, problem two is, no, let me back up. Problem one is all about oscillators in general, all kind of what we learned from M's and X's, like all about displacement of a mass on a spring. Then problem two, you're reminded of the lab and reminded that the way all this oscillation stuff works, it doesn't have to be X, it doesn't even have to be Z, it could be theta, and we could still have oscillation like in a pendulum, right? Like that's problem 2. Now here's the thing in problem 2. In problem 2, you're expected to know things about pendulums, you're expected to show things still about how harmonic oscillation refers to a pendulum. You're even asked to prove in the very last bit of problem 2, you're asked to prove, yeah, you're like all of problem 2 is about, okay, what if our harmonic oscillator is relative to theta, not Z, not X, not R, but theta, right? This is all harmonic oscillation. Well, in problem 2, what you eventually, you're even asked to show why we believe that that differential equation applies. Like you're showing why we believe it's a harmonic oscillator. And, and, and somewhere in there, you show that angular frequency is the square root of G over L. And you get the angular frequency in part B or something of problem 2, right? Well, the thing is, like you get it as a number. You get it, it's like the square root of whatever's in the, right? But you know, if you're putting this together, you know that the angular frequency of a pendulum is the square root of G over L. Or put another way, you might remember from lab that the period of a pendulum is 2 pi times the square root of L over G. Same, equivalent. If either one makes sense to you, then hear me out for a second. You have in problem 2 an expression for the angular frequency that you got by just doing the math. Like you didn't assume anything about G, you just got it. But you know that angular frequency equals square root of G over L. The problem 2 at the beginning says, assume that you're not on the surface of the earth. Assume that you're way deep buried below the earth somewhere. It says that for a reason. It says that so that you don't assume 9.8 anywhere in the problem. You just do your thing and you get your answers. You're not assuming 9.8. You're getting an answer for angular frequency in part B of problem 2. You're just getting it, whatever it is. But the thing is, it does have to equal the square root of G over L. So what I'm really telling you now straight up is the one thing that no one could know unless they were paying attention to class right now is whatever angular frequency you get in problem 2 is the square root of G over L, right? Or put it, or you could flip it around and say it the other way, but it is the square root of G over L. If you literally look at the omega that you get in problem 2 and you plug in the L and like solve for G, I'm telling you right now, if you did that as a check on your work and solve for G, you won't get 9.8. You might even be smart enough to do that and to think, uh-oh, I'm doing something wrong. But you won't get 9.8 because it says at the beginning of the problem that you shouldn't, because you're somewhere below the surface of the earth. In fact, if you're doing things correctly, you should get from problem 2 that G is something less than 9.8, bigger than 0, but less than 9.8. Okay. In the very last question of the whole exam, part C of problem 3, it says, okay, where was that pendulum after all in problem 2? It's, if you're paying attention to me now, it's not meant to be a trick. It's really straightforward if and when you get it, which you'll get it if you're hearing me now. But if you don't get it, you won't get it. What I'm saying is in problem 2, you have an omega and you know that omega is equal to square root of G over L. Solve for the G that you get and notice, well, yeah, solve for the G that you get. And to put it as bluntly as I can, okay, solve. i.e., what we're saying, if you follow what you did, and I see it's 4:15, we have like 5 minutes, so this is kind of perfect, I think. If you follow what you churned and worked hard at in part A of problem 3, you'll understand your final conclusion in part A of problem 3. You're concluding that the weight of an object is directly proportional to its displacement from the center of planet Earth, as long as it's inside planet Earth, right? Like outside Earth, our weight gets less and less as we get farther and farther from Earth. But inside Earth, what you're showing in part A is that as you get farther and farther from the center, your gravity, your weight, the pull of gravity on you, your mg, your GMM over blah, blah, goes bigger and bigger. It's directly proportional to R. So that if you're at 0, your weight is 0. If you are to half of the Earth's radius, your weight will be half of what it normally is. Like literally, that's what it's saying. It's directly proportional. It's saying that that cool, easy thing is true under these complicated conditions. That if you go a third of the way to the surface of the Earth, your G value will be a third of what it usually is. If it's usually 9.8, then it'll be like 3.3. If you go a third, that's what you're saying. That's what you're arguing in part A of problem 3. Therefore, to tie the whole test up and finish it and show up to class on Wednesday, in part 3, when it says, well, where was that freaking pendulum after all in problem 2? What we're really getting at is solve for the G that you get in problem 2. If you're doing these correctly, you won't get 9.8. You won't get 10. Let's just call it 10 for a second for ease. You won't get 10. Say you get 4. Say you get 4 in problem as your G value based on what you did in problem 2. If you get 4, then what you're telling me, if you're following this, is that that pendulum was 40% of the way out to the surface of the Earth, i.e. 4/10. Why? Because gravity at the surface of the Earth is 10. I mean, it's 9.8, but it's 10. So if you get 4, so this is saying that the gravitational effect is linear, is directly proportional to distance from the center. So if your G value for problem 2 is 1/8 the normal value of G, then you're 1/8 from the center. That's all I'm looking for. It's that simple. If you get it, if you hear me right now, and if you do, good. I mean, like, because you're like sitting in the middle of class and a little test. So why shouldn't you get a benefit for that? But that's the answer to problem. That's how you get problem C. Again, the more you get this, just show that you get it. But that's what's going on in part C. Now, okay, fairly or unfairly, what I basically just did was answer a lot of the questions that came up in the other class, but they were kind of what I would have thought I needed to talk about. I don't think I've seen any other corrections or errors in the test yet, besides these ones I've mentioned. But we still have like 3 minutes, and I will stay till everybody. So other questions about the test, any about grades or any, I mean, sorry to take so, but any questions about the test or expectations or procedures or physics? Oh, okay, cool. Yes. Any other, do people be, okay. But yeah, I mean, I think you guys should be in good shape. Again, if, well, yeah, I don't know. If there's no other, so I have a class at 4:30, but I'm going to stay like for whatever last question. So I guess I'm saying if you guys are good, okay, cool. Is there anything else I'm forgetting? I think. Oh yeah, last thing well, again, I hope this didn't confuse people. I've been trying to clean up and reorganize the Google Classroom as we go. If ever you see any homework assignment, whatever it was due, don't, especially if it was a turn in the game, like still turn it in. And you can estimate. I mean, this came up in the other class too. Like I'm just trying to have there be a portal for every class day that existed. So if you know that we were doing midterm review last week and you asked a question about cosines, but you don't remember exactly which day it was or what, that's okay. Like, just don't submit it twice, submit it once, don't say that you did it every day. But this is all like about self-checking in and self-reflection and trust. Like you can't overly lie about this game thing without me knowing it. So you're not trying to prove anything, just use your intuition. But if there's no other questions, you guys can go and I'll just wait and answer any quick questions right here. But if you're good, I'm good. And good luck. I mean, bye. Okay. Good job, everyone. Good job. Bye.
Thank you, Professor. See you Wednesday.
See you Wednesday. Thank you. Okay. Bye. Thank you. Bye.
Okay, Professor, let's talk. I need you to see how stressed out I am over this because I don't get it. I do not get this. Okay, so I was up, like, okay, I was with you when you got up to the point where M2 is the small m, and then gravity, the gravity that it experiences is everything underneath it, because the big thing has no gravity because it's uniformly dense.
So, you're good so far. Yeah, this whole thing cancels out. Yeah, good so far. Yes, yes.
Okay, then I don't understand where this r cubed came from equals m2a. Why is it m2?
Oh, wait. Oh, okay. The RQ. Okay, I can do that. Yeah, I did skip that today. That's it. I'll do that slower right now if I can. That is in the notes from the whatever solutions. But yeah. Okay, I see what you're saying. Hold on a second.
Oh, maybe I should just read. Reading
No,
is
it's
fun.
okay, but no, it's better to. I mean, no, I just mean that to say that this you'll also see this when you go over and like looking at stuff. But no, it's good for me to answer now because right, no, it's a lot, but it'll make more sense for me to say now that right when you're asking for sure. Hold on. So I'm saying this. So do you get me that M enclosed MENC that forget how I get, but you get that it refers to the ball on.
Yes.
Okay.
Yeah.
So this is what I do then. This is where and you get 1,000,000 points for doing the video right now and everything, by the way. I'm totally psyched. But, all right. So this again is a uniform density thing where it's like what we want is we want to know like what is that M enclosed? We don't know what it is offhand. We can't call it a given because its size depends on where we're standing. Like if we were standing right at 0, if lowercase r was 0, then M enclosed would be nothing. Like there's nothing below our feet. But if we're way out there, all the way at the edge, then M enclosed is the whole thing. But like, so what M enclosed is depends on how far lowercase r is. Does that make sense? So does that make sense? Okay.
Yeah.
Okay. So I want an expression. What I want to find is how it's related to lowercase r. So this is what I do. I say, well, M enclosed is to the volume enclosed, like whatever volume that ball is, that ratio must be the same, as the entire M, call M1, is to the entire volume. Like this is the uniform density thing now. For any two equal chunks of volume I pick have to have equal chunks of mass because everything is uniformly dense. So if I picked a chunk of volume over here that was twice as some chunk of volume over there, I would believe that you would have twice as much mass. I mean, that's what this proportionality is trying to say, because I believe that everything is the same thickness throughout the whole ball. Does that make sense so far? Okay. Therefore, I go, okay, so M enclosed is equal to the total M over the total M over the total volume times the volume enclosed. I just multiply both sides by VENC. Okay. All right. And now here, and we're almost there, believe it or not. Yeah, we're almost there. So go to the next page. I'm just going to recopy the top so you can see. So I have this.
Professor, I'm sorry to interrupt. I just wanted to make sure, will you be available by email if we need you?
Oh, sorry. I didn't even see. I'm sorry. Yeah, but here's what I've definitely found now is if at all possible, you can make it a note or a comment or whatever anywhere in the Google Classroom, or if you, I will get it much. I now trust that if you somehow, like even if in your exam, even if you just write a comment, I'll get notified about Google Classroom and I will answer a lot faster, or I will answer if you do it that way. But yes, if you did an email, I would try to answer, but I'm really still very bad with email. So try through the Google Classroom, or I'll write this down again, or text me for real, any of the three of you, because
Okay,
I'm
thank you so much.
no problem. Okay, no problem.
Thank Thank you. Enjoy the rest of your day.
Okay, you too. Cool. Okay. So I have this. We're almost there, Ardell, but we have this. So here I just go like this now. I go, okay, M1 was a given. Volume of the whole M1, like that means the entire total volume of that sphere. Well, any sphere is 4/3 pi r cubed. Like that's the entire volume. So I use the capital R there, but I multiply this whole thing by the volume. Pi r cubed. This is where it's coming from.
And then they just cancel.
Right.
Wait,
Right. That's where, yeah, exactly. Does that make sense?
yeah. Okay.
I guarantee the fact that if you get that, if you do, I promise you half the class is not even up to having asked what you just asked. Like you don't get it less than they do. You get it more if you get that now, seriously. And it's not just because of it. And it's not because we share ADHD, I promise. Although maybe it is partly. But does that make sense for now? Is that
Yes, it does. It makes more sense now.
All right, I'm gonna hop off just because the other class is like pounding in and out of it. I'm gonna.
Yeah, that's fine. I'll also read the notes. So that reading is fundamental. I know that.
All right, cool. I know you will. And text if then anybody who's a text if there's a problem, I'll know who you are.
Okay. All right. Bye-bye.